We are Team Pseudo RMRF, and we present our methodology for completing the final race as part of ENAE788M, Hands-On Aerial Robotics at the University of Maryland. Our team is comprised of graduate students Animesh Shastri, Abhishek Shastri, and Nicholas Ream. As a part of this semester-long project geared towards sensing and computer vision used in aerial robotics, we are tasked with completing a simple obstacle course with our autonomous Quadrotor platform. The course that we must complete includes takeoff, followed by detection and navigation over a featured wall. Next, the Quadrotor must detect and navigate through a relatively small window of unknown location and orientation. The Quadrotor must then successfully detect a small bridge used to cross a simulated river. Why we need to cross a bridge with a flying vehicle remains unknown. The next task is to land on a circular target located across the river and take off again to avoid another wall similar to the first. Finally, the Quadrotor must detect and land on a square target. Pictured here are the approximate locations of the obstacles in the netted flying facility. Each obstacle is susceptible to a randomized position not to exceed 0.6 meters in any direction and plus or minus roughly 15-degree variation in orientation. To complete this obstacle course, we must fly with the PRG Husky autonomous Quadrotor platform. This vehicle is a heavily modified Parrot Bebop 2 drone with the addition of an Intel upboard for onboard computation, forward-facing Leopard imaging camera, and downward-facing Duo 3D stereo camera. We first present our results in the form of a complete flight through the obstacle course. After optimization of our method, which will be described in the rest of this presentation, we are able to complete the course in just under 1 minute with approximately 95% success rate. Pictured on screen are the forward and downward-facing camera feeds performing obstacle detection throughout the flight. We have also included the system performance throughout the flight. The complete software for vision, high-level decision, and control runs on the Intel upboard mounted on the Bebop as an onboard processor. The overall system consists of 3 primary layers of nodes and a single topic that manages when a particular set of nodes are executed. The outer layer is the detection layer. The nodes inside it take in the raw images from the front monocular camera and bottom stereo camera. It processes the images and detects the objects of interest corresponding to the active mission. Pose information is then obtained from the detected object, which is then transformed into inertial coordinates and sent to the middle layer. Inside this layer, the corresponding EKF node takes in the raw poses and filters out the unreliable ones. The filtered or trustworthy pose information of the object of interest is then passed on to the inner layer, comprised of mission nodes that generate the appropriate reference poses for the controller, so that the active mission is successfully completed. Only the nodes in this layer have the access to change the data in the mission index topic, and consequently decides to kill itself and activate the next mission. All of the missions, like flying over the wall or through the window, or landing over a target, have the same sequential structure. The mission either starts with a takeoff command or with the completion of the previous mission. Next, the mission follows a 3-step process that generates appropriate reference signals for the controller in the form of desired pose. The transition from the search to converge step occurs on the first reliable detection of the object. The action of moving to the waypoint before the object is denoted the converge step, and upon moving within acceptable bounds on position and velocity, the next step, called the execute step, effectively generates a waypoint located beyond the object. After the completion of the execute step, the mission either ends itself and calls the next mission or lands the Quadrotor. A standard EKF is used as an observer in most cases, but here it is used to filter out false detections provided by the vision algorithms. A reliable detection can be defined as one where a series of detections happen within a short period of time. For example, 10 detections in 1 second can be safely considered reliable. On the other hand, detections that happen very rarely cannot be trusted. Hence, the EKF, by the virtue of having covariance as a part of its state, is used here to measure the detection reliability and to supply only trustworthy measurements to the mission node. We use a simple proportional derivative control law using the Bebop's onboard odometry as feedback. Waypoints are published to the controller as reference commands. An error is then generated and its magnitude is saturated upon crossing a desired threshold before transforming it into the desired body velocity commands by the PD control law. The saturation is done primarily to improve the odometry feedback, as faster motions result in inaccurate flow and sonar measurements. Also, the vision is more accurate if the vehicle is close to hover state. It should be noted that the Bebop driver publishes odometry at a rate of only 5 Hz, which is the limiting factor in terms of performance. The first task of the mission is to avoid a low-featured wall. Our method involves a stereo construction of images to estimate features and their depth through motion of the quadrotor. After sufficient reading of the wall are taken, a waypoint before the wall is published to the controller and the vehicle converges to this point. A new waypoint beyond the wall is then published and the quadrotor traverses over the wall. The front-facing camera is monocular and hence cannot estimate depth directly. However, a known camera motion can be used to construct a stereo image pair and compute depth, assuming the camera motion or the vehicle's odometry is reliable and that the scene is static. We have used the orb feature extraction and matching algorithm between 2 consecutive images to get the sparse depth information, which is then thresholded in the depth axis to get the feature points lying on the wall. The extremes of these features in the image plane gives us an estimate of the wall's edges, which are then transformed into real-world coordinates using the average of all the features' depth. A binary decision based on the height of the upper edge generates the desired pose either above or below the wall. The next task of the mission is to detect and fly through a yellow window of known dimensions. This task begins with a spiral search in the yaw-z plane until the EKF converges on the window within a predefined acceptance criteria. A waypoint just before the window is published for the quadrotor to traverse to, while the window pose is continuously updated. After further convergence on the window, a waypoint beyond the window is published. While the quadrotor travels through the window, additional feedback introduces bias to the further waypoint to prevent collision with the window. This bias is computed through the remaining visible areas of the window in frame, if any. The forward-facing video feed is converted to HSV color space and a small Gaussian blur is applied to reduce noise. A simple color thresholding is applied as opposed to something like GMM, which was found to be difficult to tune on the fly, and its implementation was found to be computationally costly. The binary image is eroded and dilated to further reduce noise. The largest contour is taken and a polygon is fit to it. The corners of this polygon are sorted and fed into a perspective endpoint algorithm, which solves for the pose of the window in the reference frame of the camera. This pose estimate is converted into the global inertial frame, which is filtered by the EKF for this mission. After the window, the quadrotor must fly over a bridge and avoid flying over the simulated river. Because its position relative to the window is generally known, the search consists of a simple yaw after the window and forward search until the bridge is in frame of the downward-facing camera. The detected bridge pose allows for the generation of a waypoint just before the bridge, which the quadrotor travels to. After converging on this point, a new waypoint is published to the controller after the bridge, and the quadrotor crosses successfully. A creative method must be used to detect the bridge since the downward-facing camera is only grayscale. First, edges are detected using a canny edge detector, which are then heavily dilated. This produces a binary mask of areas in the image which are not featured. Of the featureless areas, a simple brightness thresholding is applied to isolate the bridge, which is brighter in color than any other featureless areas in frame. A polygon is fit to the largest contour, and its proportions allow us to solve for its pose and position with respect to the camera. The next task is to land on a circular target. Like the bridge search, a simple yaw and forward search until the target is in frame of the downward-facing camera is sufficient because the target location is generally known. After detection of the target, the quadrotor converges to a waypoint just above the target and then lands. Since the target, composed of concentric circles, is printed on a white glossy paper, a simple thresholding combined with erosion and dilation eliminates the background. Next, a standard canny edge and Huff circle fitting with relaxed parameters gives a lot of circles which are then averaged to get a very reliable center and mean radius of the target. This information is then fed into an approximate perspective 2-point algorithm to get the target's position. After takeoff from the circular target, the quadrotor must navigate through a high-featured wall. This process follows the same approach as the first wall. Finally, the quadrotor must land on a square target, very similar to the first circular target. After the wall, a simple yaw and forward search is sufficient to guarantee the target is in frame of the downward-facing camera. Landing on the target is an identical process to the first. Just like the bullseye target, the concentric square target can also be detected with the same Huff circle fitting algorithm but with more relaxed circle fitting threshold. By using the same detection node as the circular target, we reduce the required onboard computation. We would like to thank course instructors Nitin Sanket and Chahat Sinj for their support and flexibility throughout this course. We would also like to thank the Computer Science and Aerospace departments at the University of Maryland for making this course available to students this semester. Thank you.